A strategic research cluster, or SRC, is a coordinated effort between individual R&D projects to produce a significant demonstration of specific technologies. The Space Robotics SRC aims to lay the foundations for high-impact and highly consistent capabilities to enable major advances in on-orbit servicing and planetary exploration, and increasing the competitiveness of the European sector.
So the challenge is to enable major advances in robotics technology for space, to allow on-orbit satellite servicing, refueling, reconfiguration, and surface robotics, so for planetary surfaces for exploration of our solar system. One important objective is also to increase the competitiveness and capacity of European space industry and space research institutes to compete on the international scene and to ultimately generate products and satellites that are stay competitive on the world market.
The aims of the SRC are captured in the PERASPERA roadmap, which charts the development of basic technologies known as common building blocks to the validation of high-impact applications via an in-orbit demonstrator and planetary analog demonstrator. These new capabilities will realize a fundamentally different vision for space markets and applications over the next decade, enabling new types of missions for both commercial and scientific purposes, which would not be possible without intelligent robotics. You may have heard the phrase new space ecosystem before, but what does it mean? For the Space Robotics SRC, it means building a sustainable and flexible space sector by using robotic common building blocks. This standardized approach will enable users to do more with their spacecraft, creating better efficiency savings and long-term returns, strengthening the space and the space-enabled economy. Over time, robots will enable us to use space and the vehicles in space in innovative new ways, opening up new markets and ideas. Future applications of robots in space could be allowing satellites to service each other in orbit, or perhaps build things robotically in space, such as telescopes and mirrors. Eventually, we could see entire spacecraft made from these building blocks, meaning they could change shape, form, and function, being robotically reconfigured to suit the user's needs. Think of it as like having your own Lego kit in space, all connected using USB cables, because once you have a universal connectivity, you can do pretty much anything. Having robots that can think and act autonomously and connect to each other to exchange data, modules, or to create a new functional form entirely means that next-generation spacecraft and vehicles such as rovers will live longer, explore farther, and deliver greater returns for us. For example, currently satellites have to carry everything they need for the rest of their life. Enough energy, power, and fuel to last a lifetime. This takes up significant amounts of onboard volume and mass, meaning less space for the tools and payloads needed for the actual mission. But with advanced robotics, satellites could be maintained and refueled by servicer spacecraft, meaning they can store more mission-relevant tools, hardware, and payloads to deliver greater scientific and commercial returns. Robotic servicer spacecraft can also ensure that, once they're finally at the end of their operational lives, satellites can be safely recycled or deorbited, leaving Earth's orbit uncluttered and safe. Just as robots are used in industry on Earth to build and assemble many of the products we use in our everyday lives, we can expect them to play a much greater role in actually building and assembling products in space. This will mean we're able to build much larger things, telescopes, space stations, and even new spacecraft that can change form and function. Together, these robotics technologies will redefine the way in which we use space and how it affects our lives back on Earth. The SRC is key to developing technologies to strengthen the European space robotics industry, and plans to go from strength to strength over the next decade. While satellites have become crucial to our modern economy by delivering services such as mobile communications and television, it is the inspirational endeavour of exploration that will enable humans to improve our understanding of the universe and take the next step in the evolution of our species. Human exploration of space has always been at the forefront of space science and engineering, but to take the next giant leap will require advancements in the field of robotics and autonomy. But Mars, like the Moon, is a big place and will require a number of different rovers and robots to explore it thoroughly. And that's where the Space Robotics Strategic Research Cluster, or SRC for short, comes in. The Space Robotics SRC is developing a suite of common, standardized capabilities or building blocks that will efficiently produce an array of different rovers that can be deployed in a variety of exploration scenarios. But current rovers can only travel a few tens of meters per sol because most sites of scientific interest are some way from the landing site and, because they're unable to evaluate the risks around them, they must wait for plans and commands from Earth, which takes a long time. By improving a rover's decision-making capability, we can create robots that don't necessarily have to rely on frequent planning from Earth. They can make their own decisions. Whereas a mission that would cover a kilometre of distance took days or even weeks, rovers with this kind of capability will be able to cover the same ground in just one day. What's more, last generation rovers were limited to predetermined paths, meaning that they could miss interesting sites. To maximise the scientific returns from future exploration missions, intelligent rovers will be able to identify points of interest by themselves, then deviate from predetermined paths to undertake new scientific investigations of areas or objects that controllers on Earth might miss. Also, current rovers aren't able to explore certain areas such as cliffs or craters for science, or even surveying lava tubes for habitability. It's just too difficult. But by using specialised rovers that can cooperate, think and act in groups, they can work together to figure out how to enter these tricky areas and then explore them. Exploration of difficult areas is not the only scenario in which cooperative robots are needed. If we eventually want to build the basic infrastructure needed to establish bases on the Moon and Mars, such as landing pads, storage space and habitation modules, cooperative robots will have to complete construction tasks using the resources they have to hand in the mission environment. Once that is in place, these little robots will have helped us to take those tentative but crucial next steps into improving our understanding of the universe, our origins, and ultimately, our destiny. The ambition of the SRC is to lay the groundwork for such missions, and to put the European space sector at the forefront of space exploration. The SRC is made up of 3 types of participant: the PERASPERA team, who manage the roadmap and the overall programme, the European Commission, which provides the funding, and several consortia of industry and academia who undertake the R&D to make it all possible. It's this unique structure that makes the SRC so effective at tackling long-term problems for the sector.
So this cluster is an ecosystem. It is a partnership of European actors in space robotics. It brings together the European Commission, the European and national space agencies, industry, academia, research organization, in a coordinated effort to enhance the use of robotic technologies in space. The unique characteristic of this cluster is that we follow a roadmap-based approach. The roadmap is provided by a consortium of the European and national space agencies that also provide technical support to the cluster. And then, of course, we have the operational layer, which is composed of grants that are responsible for technology development. And what is also very interesting is that these grants are tightly interconnected. So they are not only exchanging, but also reusing results.
Each individual research project in the SRC is funded by an operational grant provided by the European Commission through open competitions. The PERASPERA team created the roadmap to identify certain standardized technologies, called common building blocks, which would be produced by these projects in such a way that they could be intelligently and functionally integrated together. This enables subsequent projects, also funded by operational grants, to instantly integrate and use the technologies for pertinent applications, creating a hugely efficient and market-focused program of research.
The main goal is to develop a framework for the development of robotic applications in a lab environment at industry and space level. This framework is based on the use of the latest technologies, use of model-driven architecture, robotic modeling technologies, as well as integrated modular avionics and correct-by-design techniques.
It can foster the development of a new generation of robots, and it can ease the process of migrating laboratory prototypes into products, both for space and terrestrial applications.
The need for robots in industry is rapidly increasing, as ROCOS will allow for safer robotic systems in several domains where human safety is critical, like space, nuclear, search and rescue. A framework like the one proposed can have a positive effect on the competitivity for the whole industry.
The ERGO project will achieve a highly autonomous space robotics controller.
Because it will provide a new breed of autonomous system capable of handling the complexity related to mission planning with the limitation of onboard computers.
It will strengthen the competitiveness of European industry. ERGO will create new market opportunities and will increase the interest and trust of European society in autonomous robots domain.
distinguishable from the many other points of light Voyager would see, nearby planets, far-off suns. But precisely because of the obscurity of our world thus revealed, such a picture might be worth having. It had been well understood by the scientists and philosophers of classical antiquity that the Earth was a mere point in a vast, encompassing cosmos.
CROM is a development of a multifunctional spacecraft interface. It will generate significant benefits in cost reduction and functionality expansion. It has the capability to couple payloads to payloads, payloads to robotic manipulators, and client to the server. It will see applications in both on-orbit servicing and planetary exploration. The standard interface provides mechanical interconnections, as well as thermal transfer, data connections, and electrical power connections. It's a standardized building block for payload modules. The mating stage is performed by an active CROM A docking a passive CROM B. This redundancy concept allows to connect two CROMs even if one of them is damaged or inactive. The guiding petals will help correct any misalignment between both CROMs throughout the mating stage. Once the latching is completed, both dust covers from active and passive CROMs will open and both connector plates will translate to get connected. CROM's interface will allow manipulation of payloads in a planetary surface exploration, where robotic systems need to manipulate objects in order to perform scientific investigations and experiments. For on-orbit application, the use of CROM interface can go from satellite servicing or satellites refueling to assembly of modular and reconfigurable satellites. CROM interface could allow direct interaction between cooperative structures for service operations, such as maintenance and construction work on a technical infrastructure. CROM in the long term will reduce spacecraft cost and risk of failure, extend spacecraft life, improve spacecraft performance and capabilities, and foster new space business plans and allow faster response to business needs.
The main goal is to enable the highest possible level of on-ground validation of the space robotic cluster technologies in the most relevant environment. This is obtained by adapting and providing the best available European test facilities needed by each technology. It is a proven fact that space missions need always more robotic technologies. The Facilitators project allows the highest possible level of on-ground validation, and therefore it permits to gain the necessary confidence for their application in future space missions.
All European industries working in robotics can take advantage of this project. Moreover, robotic technologies which are enabled by this project are entering in our daily life, and therefore the activity can have a direct impact in the future of many European citizens.
The 2018 round of projects aims to reuse and evolve the common building block technologies in an intelligent way for specific applications. 5 different consortia, each funded by operational grants, will use the common building blocks to create intelligent, autonomous, robotic capabilities for on-orbit services, on-orbit assembly of large structures, reconfigurable satellites, long-range planetary exploration and opportunistic science, and multi-robot interaction and cooperation on planetary surfaces. These areas reflect the next generation of missions expected to be achieved by the space sector, and thus reflect the long-term vision that sits at the heart of the SRC.
Space satellites are the only complex system without maintenance. With orbital servicing, we are able to change all the full space ecosystem. We can extend the life of the satellites, we can repair, upgrade and deorbit in them, and opening up a whole new market for space.
To unlock the secrets of the universe, we need to be able to see farther into it, and that requires bigger telescopes, certainly bigger than Hubble, and even bigger than the James Webb Space Telescope. But James Webb is currently the biggest single structure that can be deployed from a spacecraft. Using bigger rockets isn't really a viable option. So, if we want to be able to take advantage of bigger telescopes and new infrastructure in space, we need to be able to build them in space. To do that, we need to use adaptable, intelligent robotic systems that are able to put together modular infrastructure by themselves.
To optimize the commercial and scientific gains from space, humanity needs to move towards the ambition of creating entire platforms that can change shape, form and function. This enables the next generation of business in space.
So far as we know, Mars is the only planet that's populated entirely by robots. But even the most capable of these robots are only capable of travelling 10 meters per day. Improved decision making will enable new types of robots to travel up to 1 kilometer per day. And that means that the scientific return that we can get from future missions will be absolutely unprecedented.
If we really want to dream of a future beyond planet Earth, you need to lay the foundation from now of a future extraterrestrial colonization. Landing zone, infrastructure, inhabitation, storage. They might seem as mundane things, but in reality they are very essential if we are serious to make this giant leap for the mankind. But now we cannot do this alone. We need some sort of robotic intelligent companion that are able to cooperate together to pave the way for us.